This lecture, we're going to look at some basic rules of drawing mechanisms, which is the cornerstone of the class. So if curly arrows and mechanisms were an issue in Organic Chemistry 1, it'll be a big part of Organic Chemistry 2. So let me know if there's anything I can do, anything more I can do to help you kind of catch up. To do this, though, to get caught up and get comfortable with these things, we're going to review SN2 and then SN1E1 mechanisms. Okay. So what we're doing with an SN2 reaction is we are doing a substitution with no intermediates. Zero intermediates. Okay. So for example, we looked at a reaction where we had, whoops, that's not right. We need a C in there. Sorry. Okay, there we go. And we had a carbon with a bromine attached to it, and then a propyl chain, right? So we have delta minus on the bromine and delta plus on the carbon attached to bromine because bromine is more electronegative. And then what we can do is recognize that opposites attract. The negative is going to engage the delta positive and push the electrons onto the bromine. So you want to draw that curly arrow starting at either the lone pair on the nucleophile, and that would be this thing right here, nuke minus. So you want to start at the lone pair or the negative charge and then attack the carbon atom to which that oxygen is going to be bonded. We use the delta positive to direct our eye towards that carbon as opposed to the other two carbons in the molecule. And then we show the loss of bromine. We need to show those two steps together because if we didn't let the bromine leave, carbon would exceed its octet. So we add one arrow from the negative. We attack either a positive or a delta positive or an acidic hydrogen, for example. And then we push off the leaving group. Now, what that does is that makes the leaving group now accept more electrons, and it now has a negative charge. And then we have our bond. We can have the oxygen spinning away or toward whatever. It's the same molecule. We can draw it. We can depict that molecule in multiple ways. But we have now our product where we formed a bond between the oxygen and the carbon. I've highlighted with a dot, establishing the new bond. Now, if we do some quick formal charge calculations, so formal charge, if you recall, is group number minus number of bonds minus number of unshared electrons. Okay. So just as if we looked at CH4, for example, we would say that its formal charge is, first of all, it is in group 4 of the periodic table. I know it's atom number 6, but it's in the fourth. It's in the fourth column of the periodic table if you don't count the transition metal series. So we have group number 4. We have 4 bonds, and we have 0 unshared electrons, and that gives us an overall formal charge of 0. Now, if we look at the oxygen atom, okay, let's draw that oxygen atom a little bit better. Let's have the bond to carbon, sure. But what does the -1 mean? Well, the -1 actually comes from the formal charge. That tells us the charge of the element and actually gives us a hint of the overall charge of this ion in this case. Okay, so oxygen is 2 elements to the right of carbon. It's in group 6. It has 1 bond and it has 7 unshared electrons, 6 unshared electrons, goodness. And that comes from 3 lone pairs. So we have 2, 4, 6. I want to do it that way. Okay, 2, 4, 6 unshared electrons from the lone pairs. 6 minus 1 minus 6, that's equal to -1. Now, what about the bromine atom? Well, bromine, when we start, okay, looks like this. and it's in group 7. It's in the column 1 to the right of oxygen. I know it's down a little bit, but it's all about the column that you're in. So we're 7, and we have 1 bond, and we have 6 electrons, just like oxygen. But now because we're further to the right in the periodic table, that number becomes 0. Could write a little 0 up here, but the picture already is fine without it. So I tend to just not draw a formal charge there. But at the end of the reaction, we have Br minus. Now what that corresponds to is the bromine has absorbed 2 electrons that were once part of the covalent bond. New electrons. Okay, so we have our new electrons from, and I'm just going to, maybe I'll take this out a little bit. Okay, so that's from this bond up here, the bond that's broken. That arrow showing the movement from the bond to the atom is actually the bromine absorbing 2 electrons that were once shared between the carbon atom and the bromine atom. So it has those new electrons all to itself now. How does that change the calculation? Well, we have a group 7 element, we have 0 bonds, and we have 8 electrons. We have a full octet. That means we should be neutral, right? No, it comes down to the formal charge calculation. Okay, formal charges are central to our understanding of mechanisms. They really are just something you should try to master. If this equation is not memorized at this point, okay, and it may not be because it's been a while since we've thought about this, pause the video, make sure you know that equation, okay, because it's going to be so useful. All right, so why is formal charge so important? Well, sometimes people like to try to come up with quick rules. Why is bromine neutral? Why is bromine neutral at the start of our mechanism and negatively charged? And they'll look at it and be like, okay, wait, it absorbed 2 electrons from the bond. How did its charge go to -1? And the answer is in the formal charge calculation down here. 7 minus 0 minus 8 is -1. That's what you go to. You don't worry about rules like, okay, wait, if it absorbed 2 electrons, but its charge only went down 1, well, it's kind of technically only, it already shared, it was kind of shared 2 electrons. 1 it already had at the outset, picks up another one when it absorbs the bond. That's not stuff I want you to worry about. I want you to, if you're not sure what the charge is on an atom, is to just check using formal charge. Just lean on formal charge calculations. They happen quick. And the cool thing is, the more often you do formal charges now, the less you have to do them later. What I mean by that is you start to sort of memorize what atoms look like when they're in certain states. Like I know that in this reaction, bromine is going to be negatively charged because I've seen bromine so many times with an extra lone pair of electrons and no bonds. I've done it so many times, and it works with so many other quick calculations because it's really a simple equation. Okay, so I just can't emphasize it enough. Know and master formal charges. It'll be the foundation to you understanding mechanisms. Okay, so this was an SN2 reaction. We went through 0 intermediates. The oxygen directly attacked the carbon, and the product was formed. Bromine fell off, oxygen was attached, the product was made. Now, what about the SN1 and the E1 mechanism? So the SN1 mechanism is a little bit more of a beast. It's not like it's hard. It's a little bit more involved. So the SN1, E1, whenever you have an SN1 or E1, a little radar needs to trip in your brain to remember that you've got a cationic intermediate. And with a cationic intermediate, what we have to recall is that the leaving group leaves first. So the leaving group's actually going to leave. Now I'm going to change the reaction conditions a bit. Br, I'm going to replace my specific oxygen nucleophile with just a generic nuke minus. Okay, so the leaving group leaves first. What that means is that that arrow showing the movement of electrons onto the bromine atom, that happens first. Now I'm going to eventually get to a product that looks very similar to the substitution reaction that we saw earlier. This is going to be our SN1 product. You may recall that E1 always accompanies SN1. But let's walk before we can run. The bromine's going to fall off, and that's going to make a positively charged intermediate. The bromine has now accepted electrons. So instead of just having 3 lone pairs of electrons, which is what it started with, by the way. That's kind of the issue with sometimes drawing them and sometimes not. Sometimes it looks like they came out of nowhere. So the bond that was between carbon and bromine, both of those electrons that made up that bond jumped over to the bromine atom to give rise to this species. Now we have a positive charge, and that positive charge is prone to being attacked by a negative charge. So we're going to have the nucleophile engage the positive charge. And when we do that, we get right to the product. Leaving group leaves first. Negative attacks the positive. It always goes from negative to positive. It's a little bit opposite from our dipole arrows that we showed with the positive tail, but don't worry about that. These are not dipole arrows. These are movement of electron arrows. The positive charge is desperate for electrons, but it doesn't have electrons, so it's not going to do the attacking. It is attacked. We call this positively charged intermediate a carbocation, and it is attacked by our generic nuke. And I always draw a nuke minus to remind myself that has the negative charge, and that does the attacking. So you start your arrow at the nuke minus, and you move it towards the positive charge, not the other way around. Okay, so what happened here was instead of relying on a delta positive to encourage addition of our negatively charged nucleophile, we actually let a full-blown positive charge form, not a partial positive, a full-blown positive charge form, which attracted the nucleophile. You might say, well, there's 2 negative charges. There's a negative charge in the bromine and a negative charge in the nucleophile. Why didn't the bromine attack? Well, if it did, we would have just gone backwards in time. That is the reverse event of a first step in our mechanism. So many mechanisms have reversible steps. And what we're trying to do with a mechanism is account for the formation of the product, tell the story of the reaction. I say to you, oh, we went out and we did this reaction, we formed this new bond. How did we do it? You'd propose a mechanism. And the fact that some steps are reversible, but for some reason, everything landed towards the product, that has to do with what's called the thermodynamics of the reaction. So we won't worry about that at this point in the game. I mean, it has to do with the fact that carbon doesn't form a stable bond to bromine, and nucleophile probably forms a more stable bond. Okay. So this is the E1 product, but what about, or excuse me, the SN1 product, but what about the E1 reaction? So in the E1 reaction, we actually take that same carbocation intermediate and we form an alkene as the product. Now, what we do with the alkene is we actually lose a neighboring hydrogen to get to the alkene. So what I'm going to do is I'm going to redraw my carbocation down here. But I just want to emphasize that the SN1 and the E1 reactions always happen together because they use the same intermediates. They both use that carbocation intermediate, and the carbocation intermediate has sort of a fork in the road where some of it goes on to the SN1 product by engaging the nucleophile, and some of it actually loses hydrogen, a neighboring hydrogen. It would count, adjacent 3 bonds away if there was a hydrogen at that positive charge center, as you're thinking about counting coupling constants. And I actually picked an annoying one, I guess. That puts the double bond down here, but those 2 structures are the same. Okay, so what happens in an E1 product is we take that same carbocation intermediate and we just let a hydrogen next door to the positive charge fall off to establish the formation of an alkene. That gives rise to an H plus as our byproduct. So we actually form Br minus and H plus as a product. So both of these events are possible from that carbocation intermediate. Okay, so these are kind of the cornerstone mechanisms to the class, and they'll be important for this first section. Cornerstone mechanisms of organic chemistry 1, and they'll be really important for understanding the first bits of organic chemistry 2. I think with that, that's a nice review of some mechanisms, and I'll stop there so that we don't get kind of overwhelmed. In the next lecture, we'll look more at the Williamson ether synthesis.